So in the last lecture, we motivated the kinds of situations that we can encounter nonlinear finite element situations. Now I want to talk about how we go about solving some of those. And we're going to begin just in 1D. So really this lecture is basically a generic lecture on how do we solve nonlinear problems in 1D. Okay, so let's begin and just say that every nonlinear 1D problem can be written as follows. Okay, so all nonlinear problems in 1D can be written as f of x equal 0. I know that looks kind of boring, but that's the truth. So how about for an example? Okay, so for example, let's go ahead and consider something that looks a little like the equation that we had in FEA. How about we have kx is equal to r, right? So this is linear and easy to solve if k and f are constants. Okay, but what if instead we have k, which is a function of x, times x is equal to r, which is also a function of x, right? That could be possibly nonlinear. So what we're going to do to solve this problem is we're going to define a new function. Okay, so we're going to define a new function, and let me put this as equation 2 as well. We're going to define this new function, call it f of x, that's now equal to k of x times x minus r of x, right? Call that equation 3. Okay, the solution to 2 occurs when equation 3 is equal to 0. Right? All we did was subtract off 1 from the other side. We said that instead of kx equals k as a function of x times x equals r as a function of x, we just subtracted that off so that now this, if we want to recreate equation 2, we just set f of x equal to 0. Okay? That goes back to this equation 1, right? As in equation 1. Okay, so what does that mean? That means that therefore, solving a nonlinear problem in 1D just simply requires finding the roots of f of x. And I put simply in quotes because it's not always simple, but simply involves finding the roots of f of x. Right? That's what gives us f of x equals 0. So let's think about that. Okay, so let me just say, recall for the following, right, that for a general function f of x, we can have no roots, and in our case, that means that there's no solution. We could have one root, or we could have multiple roots. Okay? So let's kind of try to visualize what each of those cases look like. Okay, so if this is x and this is f of x, and we have a function that looks like this, right? This has no roots, right? Which means no solution. Okay? In the contrast, let's suppose we have some function here. There's x and f of x. And now we want to say, I'm going to try to draw this as best I can. It just touches this axis. Okay. So what do we have there? We have one root, one solution. Right? We could also envision other ways to have one root and one solution. Right? So we could have something that maybe looks like this, right there. And we also have one root here. And then finally you can envision how we could have multiple roots. All right, if I come down and something like that, then I have a root here, I have a root here, I have a root here. So I have multiple roots, which means I have multiple solutions. Right? So if we have this the general equation, right? So for a general function f of x, we may not be able to find the analytic solution. Okay? And so what we want to do here is we want to develop a numerical approach to finding it. Okay, so a numerical approach. And this approach is going to be iterative. Okay? Which that means that we're going to guess a solution. We're going to use that to get us to a different solution. Then we're going to use that solution to get us closer to another solution, and so on and so forth. Okay? So as we are going to cycle through lots of different possible solutions, we need some way to talk about the measure of the error of our solution. Okay? So we need a measure of the solution error. So one approach we might take is, well, let's call it the true error, right? So one way you might think about this is to look for the true error, right? Or the true relative error. Okay? And you might define the true error as equal to whatever the true solution was, we'll call it x true, minus the numerical solution, just the magnitude of that. I'll put num for numerical, okay? And if you wanted the relative error, then you take the magnitude here of x true minus the relative error, or sorry, the numerical error, divided by the true. Okay? So in the context of evaluating methods, this is the approach we might like to try. The problem is if we knew the true solution, we wouldn't need a numerical solution, right? So this is the type of error that you might want to use if you are benchmarking a numerical solution against a known analytic solution, okay? But in general, it's not that helpful because we don't usually know x true. Okay? So another type of error that is a little bit more common to use is the estimated error or the estimated relative error. Okay, so in this case, it goes like this. The estimated error, I'll put EST for estimated, is going to be equal to the magnitude of x n minus x n minus 1, where these are, the n minus 1 is the solution at the n minus 1 iteration, and then this xn is the solution at the nth iteration. So it's basically asking how far apart are our sequential answers as we iterate, okay? The relative estimated error is, as you would expect, just this quantity, the magnitude now of x n minus x of n minus 1 divided by x of n minus 1, okay? So that gives you some measure of the relative error. So this, again, it's not a perfect solution for how close you are to the real solution, but it is telling you how much your solution is moving with each iteration, which in theory, as it should, you hope, as you get closer and closer to the correct solution, it's going to move less and less and less as it approaches the value, okay? The final measure that I want to talk about, not the only one that exists, but the final that I want to talk about, is called the tolerance in f of x. And all it is it's the magnitude of how much your predicted solution differs from the approximate solution. Right, when your approximate solution is supposed to be 0. So it's the magnitude of the deviation of the approximate from 0. So we would write that as the tolerance of f is equal to the magnitude of the function f evaluated at x num, whatever that value happens to be, right? Whatever we computed. Okay, so the problem is here, this is again another reasonable measure, but it's not perfect. It may not correspond to the solution very well. Okay, so I'm not trying to disparage either the estimated error or the tolerance, but neither one is perfect, but they're all we have to work with. So usually when we're working with iterative methods, we choose either or for trying to decide when we want to stop our iterating. Okay. Let me give you an example of why that tolerancing might not be the best. So if this is my function, my real function, so there's x, and here's f of x, right? And let's say I come down here, I come over here, come down, something like that, right? I may be in this location, right? If this is my x num, the function evaluated there is very close to 0, but this is the true solution, right? And so even though I'm close in the tolerancing, in the tolerance solution, I'm not very close in my actual solution for the 0 of the function. Okay, so that's the pathology of using this. Okay. All right, so in 1D, we can basically divide the solution techniques that we might choose into two broad categories. The first is called bracketing methods, and these are going to include methods like the bisection method, the regular falsi method, etc. Okay, we're not going to talk about these methods. And the second category that includes the method we're going to discuss are what are called open methods. Okay, these are going to include broadly Newton's method, the secant method, and as well as the fixed point iteration method and others. Okay, we're going to focus on Newton's method here. Just because it's the most commonly used in FEA. Okay, so how does it work? So here's Newton's method. So the strategy or the main idea behind Newton's method is that we're going to guess a solution, and we're going to use the intersection of the tangent line at that location with the axis to select the next point. Okay, so with the axis, so we're going to guess a solution, use the intersection of the tangent line at that location with the axis. What axis are we talking about? The y equals 0, right? So crossing the x-axis. Okay, we're going to look for where it crosses there. And we're going to select that as the next point for evaluation. Okay, so we guess a solution, use the intersection of the tangent line where it crosses the axis, and then choose that intersection point as our value for our next solution guess. Okay, so it's a little bit easier, I think, to see if we let me scroll up. If we look at a picture. Okay, so let's draw a curve here. Here's x. Here's f of x. And I'm going to choose a nice curve just so I can illustrate this a little bit better. Let's suppose that we have a curve that looks something like this. So this is our curve. This is x. This is f of x. Okay? All right, so let's suppose that our first guess is at this location. Let's call that x1, right? So what I'm going to do is I go up and I look at, okay, here's my point on the curve. x1, and now I look at the tangent line at that location. So I'm going to make a dash line for the tangent. Okay, there's my tangent line, and it intersects the x-axis at this location. So that's going to be my new value, x2. Okay, so I go back up to my curve, right? So I look at that. Okay, that's my new value of f of x. I find the tangent line. I'm going to go ahead and project down now. Okay, so their intersection is there. This is my new value, x3. I go up here. There's my new point. Right? And I do the same thing, except now I'm getting very close, right? So you get the idea. So what do I want to do? Well, the first is my first guess is I need an equation for the line. This first point is x1 and f of x1, right? That's the location of that point. So I need to figure out what's the equation of a line that's tangent to the curve through that point. So let me remind you back to algebra, what the equation of a line through that point is. So there's the equation of a line through x1, f of x1. Okay. Let me also go back here, right? What's the goal here? The goal is to find this point here, right? This is x true. Okay. So what I was trying to show you was that we pick this value, and as you can see, this method gets us closer and closer to that value as we progress along, right? So x4 is probably going to be right at that x true value, or very close to it. Okay. So what's the equation for this line? Well, it's f of x minus f of x1 is equal to f prime of x1 times x minus x1. That's the equation of the line, right? So we want to know where this intersects, right? So we want to set f of x equal to 0, because that's what we're interested in, and solve for x. That becomes x2, right? So in this equation, let's call this equation, let's see, did I label my other equations? I don't think I did. It doesn't matter. We don't need to label this equation. Okay, so let's set that equal to 0, and then let this value of x, this becomes x2, and we're trying to solve for x2, right? That's our goal. So we want to solve for x2. So if I write this out, I end up with minus f of x1 is equal to f prime of x1 times x2 minus x1, right? Let me just keep going through. I'm not going to write all the equation numbers. That's negative f of x1 is equal to, I'm just going to distribute through now, f prime of x1 times x2 minus f prime of x1 times x1. I'm going to go ahead. Remember, I'm solving for f of x2, so I bring this over, and I'm left with, let's see, f prime of x1 times x1 minus, let's see, f of x1 is equal to f prime of x1 times x2. I just need to now divide by f prime of x1, and so I can get now that x2 is equal to f prime of x1 times x1 minus f of x1 divided by f prime of x1, right? Something I want to point out, let me actually finish this out. I'm going to go ahead and divide this through, and so that's equal to x1 minus f of x1 over f prime of x1, right? So that's how I would get x2. But I can extend that now and make it an iterative scheme, right? And I can, so if I want to do that, so let me generalize now. So let's generalize to the I plus 1 iteration. Okay, this is now x, the I plus 1 iteration, is equal to whatever we got from the ith iteration minus f of x evaluated at I times that derivative f prime evaluated at xi. Right? So this is the general form of Newton's method in for a 1D problem. Okay? Something I want to point out, when you look at this equation, one thing you see is that if f prime becomes small, near 0, this thing is probably going to blow up on you, and that's what you find. Okay, so if the solution occurs at a spot where the slope is shallow, so near 0, this method starts to not work very well. Okay, And so typically here, we're going to go ahead and iterate until some specified error metric hits a critical value. Right, so typically this is going to be an estimated relative error or tolerance. Okay? Let me give you some remarks about this method. Okay, number one. When Newton's method works, it works pretty quickly. It means it converges quickly. Right? It's fast, so we say it converges quickly. Okay? That's why we use it typically in FEA. Okay, number two. As you might guess, the choice of the starting point can significantly impact the efficiency and even the solvability of the solution. So efficiency and solvability, right? It's possible that we can't even solve it if we guess too poorly. Okay, number three. One thing you see from this boxed-in equation is that Newton's method requires us to calculate the derivative. This isn't always feasible or computationally efficient. Okay? And the fourth thing I want to say is that it doesn't always converge. Okay? This is particularly true if the derivative term is small near the solution point. Okay, so maybe I can illustrate this. So let's go ahead and draw a graph here. This is f of x, and here's x. Okay, so for example, if I have a solution that might do something like this, that has two solutions, right? And I chose a value. Let's say I chose my first value right in this region, right here. Well, my tangent modulus is 0 or nearly 0 there. It shoots way off back to here for my next guess, right? Who knows what the function looks like back there? It might get me further and further from the solution, right? Let me give you one more example where it's not that the derivative is small, it just happens to be the shape of the solution, or the shape of the f of x term. So what if I have something that looks like this? Well, what could happen is that I could choose a value that's in this region. So my tangent modulus now shoots off in this direction. Maybe it comes back over intersecting, let's say here, right? Now I have a solution that, let's suppose that let's draw this out further. Maybe it comes down to there. Now I project there. I want to go back. I'm trying to find that. But really my intersection comes back to here, right? And I don't know what happens. The bottom line is that my function now deviates. So anytime my f prime of x is small near my guess, it's going to shoot me off into a direction that's not helpful. And it's possible too that you can imagine, even if I get in close here, I could shoot to here and shoot to here, and I could kind of bounce back and forth around this without ever reaching the solution, or at least not very quickly. So this is a powerful technique. It's the one that's most commonly used, but it doesn't guarantee a solution. So just be aware of that. I know that's, for me personally, isn't satisfying. It's not elegant, but it is what's most commonly used. So when you run a finite element analysis and you are cursing the code because it tells you that it couldn't find a solution, then you'll know why. So with that, next thing we'll do, now that we've talked about it in 1D, moving on, the next lecture is going to be about how do we handle this with systems of equations, right? So we have a matrix, a set of matrix equations, which is a lot more pertinent to the FEA solution.